Okay, so it seems that there was a problem with the microphone, and a very important part of the lecture was recorded without a voice, so without sound. So I want to record this again, and this part of the lecture is about the Zig Zag product, which is, of course, the crucial operation among these three operations that will allow us to construct expanders and to prove SL equals L. So let's just dive in. So the zigzag product, in order to define it, I need to slightly refine my definition of, the way we are going to represent a graph. Say we are given a deregular graph, and as usual, we are going to assume that it's undirected and labeled, namely, say the graph is deregular. So from every vertex, so if you take any vertex V, then the D outgoing edges from V, or D edges touching V, it's an undirected graph, are labeled by numbers 1 through D in a bijective way, right? Every label appears once. So that's the usual notion of labeling. So given such an undirected labeled graph, we define the edge rotation map as this function. So this is a function that gets us input two things, both a vertex, and then secondly, a label, a number between 1 and D. And the output of this function is not just a vertex, as you might expect, but also a label. So in picture, what's going to happen is that, let's switch colors a bit. So if you have a vertex V, and this vertex V, its ith neighbor is some U, then U labels its neighbors in any arbitrary way you want, regardless of how V labels its neighbors. So if U consider V as its jth neighbor for some number J between 1 and D, then the result of applying, maybe I should have swiped U and V here. Sorry. So if we have a vertex U and U thinks you consider V as its ith neighbor, and then V consider U as its jth neighbor, then applying pi on U comma I will return not only V, but V comma J. Okay? So that's kind of the instruction back. So if you are at V, then if you go to neighbor J, you're just going to go back to where we started from, vertex U. And sometimes we will only care about the vertex rather than the edge label, J. We would want to kind of ignore J. And in that case, we'll put a little dot above pi. So pi dot of ui is just the projection of this function to V. Okay? So pi dot of ui is just V. And the one important thing to note is that pi is an involution. Namely, if you apply it twice, you get the identity. If you compose it with itself, you get the identity, just by definition. So with this, we are ready to define the zigzag product. So the zigzag product is a product. It gets two inputs, two graphs. One, it's kind of the main graph, and one graph which we think of as a small graph, and we kind of refer to it as the gadget or a gadget graph. So say G is a D1 regular undirected graph on N1 vertices, and we'll denote the edge rotation map of G by pi sub G. And similarly H. So H is a D2 regular graph. The crucial point here is that H, is a graph on D1 vertices, the degree of G1. Okay, so the important point to notice is that the size of H is the degree of the regularity degree of G. In any case, we are going to denote the edge rotation map of H by pi sub H. And the zigzag product of G and H is a graph. It's denoted like that, but it actually, the way to define it is we will define it using the edge rotation maps of the two graphs, and we'll actually define the edge rotation map of the resulted graph, of the zigzag graph. So this is a graph whose vertex set is this thing. So its vertex set is composed of a pair. N1 is the size, number of vertices in G, and D1 is, it's two things. It's either the degree of G or the size of H. It's the same thing. So ignoring the vertex, the edge for a while, just looking at the vertices, the way we would think of the vertices of this graph is as kind of clouds. So every vertex in G, so if you take V in G, so for every vertex in G, you will have D1 vertices, but we will kind of think of them as, living in city V, right? V is the name of the city. So V is not a vertex in the zigzag product graph. It's just the name of a bunch of vertices, common name of them. And in each such city, for every vertex V in G, you're going to have D1 vertices, just labeled by, once you know in which city you are, these are just labeled by 1 up to D1. But we think of these vertices, as labeled by, so this is V comma 1, this is V comma 2, all the way through, and this is V comma D1. Right, so for every vertex V, we have this V city, and these are the neighborhoods of the city. These are the actual vertices of the graph. Okay. Okay, and what about the edge set? Well, so the cool thing about the zigzag product is that the degree of the resulted graph has nothing to do with the degree of G, only the degree of H. Okay, so the degree of G affects the size of H that we are taking, but the degree of the zigzag graph is essentially the degree of H squared, namely D2 squared, independent of D1, the degree of G or the size of H. I mean, you may have correlations between them, maybe some conflicts between them. Maybe D2 is related to D1, but in a typical application of the zigzag product, D2 is constant and D1 is either a larger constant or non-constant. Okay, but in any case, the degree of the zigzag product is just D2 squared. And we are not going to label the neighbors by 1 up to D2 squared. Rather, we are going to label them by a pair of D2 elements in D2. This is D2. Okay. Okay, so, in order to describe the rotation map for the zigzag graph, given A and B, I need to tell you who is the A beef neighbor of a vertex. Some vertex, and recall that the vertices are these U comma I's, where we think of U as the city name and I as the neighborhood in the city. Let me remove that and I can draw a picture that will explain what's going on here. So this is the actual definition, but let's draw the picture. So we are looking at vertex U comma I. So we are living in kind of city U and vertex I. I is a number between 1 to D1. And I need to tell you what's the edge rotation map behavior on A comma B. So the first thing I'm going to do, this is item 1 here, I'm kind of going to ignore U completely. And I'm just going to ask, using A, who is the eighth neighbor of I? So this will be the same for any cloud, just regardless of U. This completely depends only on I and H. So, and the structure of H. So the first thing I'm going to do is to figure out who is the eighth neighbor of I. And note the little dot here, which means I don't really care about the way I prime thinks of I. I don't care what's kind of the A prime that leads from I prime to I. So we are going to move from I to I prime using A. Okay. And we're going to stay in the same city, but just moving within like this copy of H in the city. Note that this kind of implies implicitly that we have a copy of H sitting in every cloud, because I'm moving as instructed by H within the cloud. So that's not an edge in the zigzag graph. That's just the fourth step that determines the actual edge that's going to happen. So in the next step, I'm going to ignore B and definitely A, and I'm just going to do an intercloud step. So what do I mean? So now I'm at CTU and at vertex I prime, and I'm going to ask G, who is the I prime neighbor of U? So that's some V, and there is some J prime, which, V considers U as its J prime neighbor, unlike this step, which I didn't care much about that label back. So the picture here would be something like this. So we are moving between clouds, between cities. We are moving to some V, and there is some J prime. I'm not sure what the color coding does anymore, but we're moving to some J prime. Right, so vertex V thinks of U as its J prime neighbor, like that. And then, now given B, I'm going to move again inside this cloud from J prime to the beef neighbor of J prime according to H. Okay, so I'm going to do a step like that. Again, not sure what the colors represent anymore. And I'm going to get to J. So once you have done that, now we know that the AFB neighbor of UI is VJ. Okay, so these two vertices are connected by an edge. Right, so essentially, two vertices are connected by an edge. If there is like if there is an edge coming from H, leading you to some vertex within the same cloud, then you follow the unique vertex, the unique edge, moving out from this vertex to some other cloud, and then you take. So now for every, for any of the D2 neighbors of this vertex J prime in H, you get to some vertex, and these are the neighbors of. For every D2 choices here, you have D2 choices here. This amounts for the D2 square choices of neighbors that you have. Okay. It takes some time to make sure you digest that, but let's look at an example. So this was shamefully taken from the Huri lineal Wigderson survey. So what's going on here? So here we took the zigzag product of the grid, the infinite grid. Of course, we only took some part of it in the picture, but you should imagine that it goes on to infinity like that. So that's the grid, and you kind of see, this was a vertex, but now it becomes a city, and so forth. And we took this as G, and H, kind of the small graph, was the length 4 cycle, C4. Right, so these edges, the kind of dotted dashed edges are edges coming from H. In every cloud, you have a copy of H. And these intercloud edges are those coming from G, right? So this vertex has 4 neighbors. So they are kind of assigned to the 4 different vertices in the city. And so what's the neighbors, for example, of these vertex? Well, you take so you're going to have 4 neighbors because it's 2 squared, 2 it's the degree of C4. It's D2 in the general notation that we have. And so the reason these 4 vertices are connected, are adjacent to that vertex in the zigzag graph, as depicted by these edges, is because there is an edge coming from H, then the unique G edge, and then another H. So that's the reason why these 2 vertices are neighbors. And then because of these H, G, H steps, these 2 vertices are neighbors, and symmetrically, you have these 2 neighbors. I think the name zigzag is kind of self-explanatory. You do a zig and then a zag and so forth. If you draw it correctly, it looks like a Z also. Okay, so that's the construction. The cool thing about it is that the degree of the resulted graph has nothing to do with the degree of the original graph. So that will allow us to decrease the degree, not just decrease, like completely decouple the degree of what it was originally. The number of vertices is clear, it's just n times d1, so it increases slightly. Sometimes it's a nice artifact, and sometimes it's kind of annoyance that the graph doesn't maintain the vertex set that it had. And the important thing, of course, to ask is what's the spectral expansion of this graph? What's omega? And so the theorem that we will prove, the main theorem, is that is this bound, which is, by the way, is not tight. So it turns out that what we'll show is that omega of the zigzag graph is at most omega of g plus 2 omega of h. It kind of makes sense, or there is some karma to it, because you do 2 h steps and 1 g steps, so you would imagine something like that maybe. Also know that you cannot have like no dependence of omega h, because the degree has degree is inherited from h, and by the Alon-Lopana bound we know that there is a bound on omega in terms of the degree. So you should definitely expect at least an appearance of omega h, potentially better than 2 omega h. And usually what will happen is that omega g is actually small. Omega h or 2 omega h is like the main contribution of this from this bound. Okay, so we're going to prove this theorem, and already here I'm going to tell you that this bound is not tight. In fact, we will prove something that's stronger, but we're just to keep the computation simple, simpler. We will just show this bound, but actually what we are showing is a bound on gamma. So if we denote by gamma of any graph of the complement of omega, so if you want omega to be small, here you want gamma to be large, close to 1, then what we will actually prove is that gamma of the zigzag product, which you want to be large, is at least gamma of g times gamma of h squared. So it also kind of follows the same karma, 1 step of g, 2 steps of h. But it turns out, if you just plug this in, it turns out that this is a stronger bound. Just because you have these quadratic things that are lying there. And sometimes it's important, sometimes it's not. When we'll prove SL equals L, it will be useful that that's the case. For the construction of expanders, it doesn't really matter. Okay, so let's start proving this theorem. So the first thing to do is, in general, that's a general rule of thumb in spectral graph theory. The first thing you want to do is to, you just define this kind of combinatorial or even algorithmic in nature kind of construction. I told you what to do and so forth. It's not very spectral or linear algebraic in the way it looks. So the first thing you want to do is to kind of construct an operator that captures this algorithm or this description of the graph. And to do that, we are going to, you see that G is of size n, but actually we think of what you want to do, kind of lift G to kind of break it apart to n times d1 vertices, because as you see in this picture, every vertex in G was kind of split into n times d1. d1, it's degree in this context. Vertices, so you kind of want to do that. We kind of want to break G in the grid, for example, it was like that, to just these edges. Right, so we want to take from G to break it apart in the sense that we are only going to see like d1 times the number of vertices that were originally in G, but we only want to see edgewise these edges. So we really want to find this matching, perfect matching from G. You want to extract it, and that's exactly this matrix. So we are going to define P. So P is going to be an n times d1 matrix. You see you have a city and a neighborhood in the city, u comma I, indexing both rows and columns. So P at entry u comma I, v comma j is 1 exactly when the edge rotation map tells you that UI is when applying the edge rotation on UI, you get Vj. So that's a perfect matching because by the way we define it, if you go from UI to Vj, then applying it again, you go back to UI, and every pair like that has a pair that's paired to it. It's a function. So again, in this case, if you keep in mind, instead of having like vertices and they have like four adjacent vertices, you have n times d1 vertices, but the edges are perfect matchings, kind of representing the edge rotation map rather than the like only the graph in some sense. It's the same thing. They encode the same information, but it's a matter of presentation. Okay, so that will be useful in order to describe the G step that we are doing. As for the H step, what we are going to do is we are going to define a tilde sub H as tensoring the identity on N1 elements or vertices with the adjacency matrix of H. Okay? So operator-wise, it means kind of if you choose a basis, it means that you have a block matrix and you have a copy of H in every block, zeros outside, of course. You shouldn't think of it like that. The way you should think of it really is this is the way that in operator forms that we say we have a copy of H on every cloud. Okay, and we're going to denote by A the adjacency matrix that we care about, namely that of the zigzag product graph. And with this, we have the following way of representing the adjacency matrix of the zigzag product graph. I call it the never proven claim because no one ever proves it. And it's as follows. So the adjacency matrix of the zigzag product graph is obtained by the product of these three operators, which correspond to the steps that we had. So we first have a tilde h, have or apply and so forth, a tilde h. So that kind of captures the fact that we are doing in every cloud the same thing. We take an h step, an h step. Then we do the g step, which is encoded by p. And then we do another h step, right? So if you think about it for a while or draw a picture, you will see why this is exactly the adjacency matrix of the zigzag product graph. I hope it's intuitive, but just in case you want to compare it or with the way I proved it, because no one ever writes the proof, then you can find it in these slides. Okay, I'm going to skip the proof, but it's kind of annoying and technical, and there are probably better ways of proving it. But in any case, I do want you to appreciate the fact that this algorithmic kind of in nature description of the zigzag product has a very nice a way of representing it as an operator. And if you want any hope to bound or understand the spectral expansion of an operator, you want to know what the operator is. You want to move from an algorithmic description to a more linear algebraic one. So that's this claim. Okay, so with this, assuming that we are fine with this claim, we are going to analyze this operator. Yes, so that's the proof. It ends here. And with that, we can proceed. So first of all, it's, I prefer to analyze omegas rather than lambdas, namely the normalized version. So if this is the adjacency matrix of the zigzag product graph, then this is the random walk matrix or the normalized adjacency matrix. I just normalized by, 1 over d2 squared. So a tilde h, if you normalize it by d2, you get omega tilde h, right? The I that you tensor with doesn't really affect anything in terms of normalization. And so this is the other d2 factor, and p it's just a matching. It has degree 1, so we keep it as is. So what I'm saying is that this is the random walk matrix corresponding to the zigzag product graph, and we want to figure out what's the largest second or in absolute value eigenvalue of this matrix. So it will be more convenient, slightly more convenient to work with the gammas, which I mentioned, like 1 minus omegas rather than the omegas themselves. So we are going to denote by gamma h 1 minus omega h, and same for g. And the first thing you want to do in these things is to somehow, you have this expander h, you want to break it to its kind of ideal part, j, and to e. Now, in one of the lectures, the earlier lectures, I told you that you can always write a W, if W is the random walk matrix of a, say, omega expander graph, you can write it like that. Well, actually, what I actually told you is this thing. This is the 2 norm, the operator norm, if you recall that. And the reason was just that you can just use the spectral decomposition theorem. Say it's on n vertices. Right, these are the eigenvalues and these are the eigenvectors. And the first eigenvector by regularity, and because we normalized, is the all ones, normalized all ones. So psi1 is the normalized all one, so it's like 1 over square root of n per entry. Omega 1 is 1, so you get like a 1 times j. J is the normalized all ones matrix, so it's a 1 over n, all 1 over n matrix. Every entry is like 1 over n, plus, sum I go from 2 to n, omega I psi transpose. And because this matrix, this operator has norm at most omega, because it's just sum of projections, and when you have this normalization by at most omega in absolute value, we have this equality. So you can always write W, even though W is the random walk matrix of a bounded degree graph, kind of an amazing result. You can write it as you can relate it to the random walk matrix of the complete graph with self loops, like the ideal matrix, plus some error matrix. So this is not quite a graph, but it's kind of an error matrix, and the error decays with omega. Now here we have something slightly different. So first of all, I took omega h outside of E. That's not a big deal. You can always do that. You can say, well, omega E is most omega is 1. You just put out an omega. The interesting thing is that I have like a gamma here, which is 1 minus omega, which does not appear here. So so sometimes you would prefer this description or way of presenting things, and sometimes that. But the way to see this is to just know that you can take from J a little bit, right? And you have the sum from above here, right? So I kind of split this 1 times J to 1 minus omega J plus the rest of the sum. And this again is a projection matrix that's orthogonal to those. So by the same reason as before, this matrix also has norm at most omega. And so that's why you can write it, you can just take a little bit from J outside, and that's why you can write it as gamma J, because that's gamma J plus some arrow matrix. So that's explaining this arrow, with this assumption on E. So, okay, so once we kind of broke the operator corresponding to H like that, we can plug it into kind of easily into the tensor, because omega tilde H is this I tensor omega H, tensor WH, and we can write it like that. And now we're just going to use this convention that every time you have a tilde on something, it means I tensor the thing without the tilde. So I'm going to define J tilde as I tensor J. Gamma H just goes outside. The tensor is like bilinear. And then I'm going to define E tilde of H as I tensor E. Okay? Good. By the way, maybe I should say, so the good thing about EH is that it has small norm of most 1, but that's also the case for the I tensor, right? Because the norm of the tensor is just the product of the norms, which is 1 times 1 in this case. Good. So to recap, we wrote W like that. That's before the last discussion. And then in the last discussion, we actually wrote WH tilde as really a convex combination, because the sum is one, between something which seems like ideal, we will see in a second what exactly that means combinatorially, and some error term. And then if we plug it back into this, plug it back into both places here in W, then you would get four summons. And the fourth summon corresponding to a peak in J in both cases here will result with gamma H squared, which I mentioned before, if you remember, times J tilde PJ tilde. And then there's the other three terms, which I'm just going to wrap up in this E hat, where E hat, if you just look at it for a second, you have a gamma H, omega H, and then you have either a J and an E or an E and a J. It's non-commutative, so technically you need to write both. You can try just two of those. And the last one, which is actually of smaller magnitude, is omega H squared. Typically, it's of smaller magnitude, and then you have E tilde H, P tilde H. Okay. Now, the important thing to know about this matrix is that it's also small in terms of norm, because the norm of this matrix is at most, you can use the triangle inequality. So the norm of this matrix is at most the norm of the three matrices that we see here. So we have a gamma H, omega H, and the norm of that, which is 1, because the norm of every matrix here is 1. Similarly here, and similarly here. So the norm of E hat is at most, two of those because of these two summons, and 1 omega H squared. And just, transforming this gamma to 1 minus omega, you get 2 omega H minus omega H squared. If I wanted to prove the slightly stronger result, I would stay like that, but for simplicity, let me just bound it by 2 omega H. So that's just a recap. And that's just a remark that I'm saying. It's kind of out of place. It should be actually in a later slide. So maybe we should ignore this for now. Okay, now the key observation is, okay, so we just, going back, we had this description of W. This is clearly an error matrix because it involves some sort of error, either in the left or the right or both sides. So, if we did everything correctly, this operator should be related to something which is kind of ideal. And indeed, what you can show is that J tilde PJ tilde is exactly the tensor of WG and J, like the clique. Like this is really putting a clique with self loops in every cloud rather than just H, an expander. And that makes a lot of sense, right? I mean, I'm not going to prove it formally now. It's kind of similar to the never proven claim. But the point is that, you have this cloud, you start with some cloud. So I guess what I'm really doing is I'm kind of applying this operator to some unit vector. So I'm looking at some particular vertex. So that vertex, v comma I, and therefore, without really explicitly saying that, I'm applying this operator to the matrix which indicates this particular vertex. One of the standard basis vectors. And then what will happen is the first J tilde will just pick a vertex uniformly at random here in cloud V, right? Because J tilde is like the clique with self loops. So you take one step, you don't remember where you came from. That's complete. So you kind of ready to go to a neighbor of V because you're choosing a number between 1 and D1 uniformly at random, independently of I. And then you move, you take the kind of the step, the intercloud step, as described by P. So essentially what you're doing, you're moving to a random neighbor of V in G. So maybe we moved here, move to some little j in some vertex U. Maybe, U is the ith neighbor of V in G. And then what you are doing next, I mean, now it's not completely like, everything is not completely smooth because looking at J, I know where I came from. So the second J prime, J tilde step, kind of erases this information because it chooses a neighbor of J from the clique with self loops uniformly at random. So you just pick a completely random, vertex in this cloud, which kind of erases the way you came, your steps, the way you came to you. And that's exactly correspond to that, right? Because this means you take a step I mean, when you see a tensor, it means that you do two things independently. You take a step at G according to G, right? Which is what we are doing here. And then secondly, you apply J to the second kind of buffer, the second component, which again, it kind of erases the where we came from. So that's not a proof, but that kind of explains intuitively why this claim holds, and you can prove that. You can just show that these two operators operates the same when you give them some basis, but it's nice to work with the standard basis, which is essentially what we did here. Okay, so to recap, we have that, right? So I plugged this expression which appeared here before, but I plugged it instead this one, I substituted this one. So W is, gamma h squared of something which is great plus some error, where the error is bounded by this simplified expression. Now, with that, I can actually bound omega of W, or the zigzag product graph. So to do that, I need to take any vector which is perpendicular to the all ones vector, because the graph that we obtain is clearly regular. So one is an eigenvector corresponding to this eigenvalue. And here I just forgot in the slides to normalize. So I'm assuming x is of norm 1. And all I have to do is to bound this expression, right? Because omega is the maximum over all normalized vectors that are perpendicular to the first eigenvector, which in this case you can take to be 1 because of the regularity, Wx. Right, so that's what I'm trying to bound here. So this thing, just using this knowledge we have on W, is at most gamma, and using the triangle inequality, is at most gamma h squared times the norm of this operator applied to x plus the norm of this operator applied to x. Now, this operator has small norms, so regardless of the fact that x is coming from a perpendicular, to one vector, just because the norm here is small, you get this bound on this expression. Now, this, however, has norm 1. So here it is important that x is perpendicular to the all ones vector to actually argue that the norm of this vector is opposed to that, right? And I'll let you kind of figure out why is it true that, why is it the case that for such an x that's perpendicular to the all one, really you gain this omega g, sorry. Okay, if you have trouble proving that, you can just go back to the lecture on tensoring and see how you can write x that's perpendicular to the all one, break it down, and then you'll see what's going on. But anyhow, you get this expression, and again, I'm just going for simplicity to assume that to bound it by omega g, kind of bounded this by 1 from above, plus 2 omega h, which concludes the proof. Right, so to recap, actually I can recap going backwards. So to recap, we just show the zigzag product, which completes this line. Right, so squaring had this property where it decreases the spectral gap, omega, which is great, or spectral expansion. Tensoring has this power of even squaring the number of vertices, so increases the graph size. But both of them had a kind of a bad effect on the degree. Both of them just square the degree if you took the same graph in tensoring. Zigzag, however, has this cool artifact of decreasing the degree, or actually completely decoupling the degree from the degree of the original graph. It slightly increased also the number of vertices, which we will actually use in the first construction of expanders. But it had some loss in terms of spectral gap, but a manageable one. We proved that omega of the graph becomes omega plus 2 omega h. So the new omega is at most omega g of plus 2 omega h, which will be enough for us.